For more than 100 years, we've been told a very strange story about the world. It's the story of quantum mechanics, and it says that deep down, reality is a ghostly, uncertain place where particles can be in many places at once, and the universe is constantly rolling the dice. This story gave us lasers, microchips, and our entire digital world. But what if one of the smartest people on the planet, a physicist who won the Nobel Prize for helping write that very story, is now telling us we might have the most important chapter wrong? Gerard T. Hooft, a living legend in theoretical physics, is posing a profound challenge to the theory he helped build. He argues that the weirdness we've all heard about, the spooky and random nature of the quantum world, isn't a feature of reality. He thinks it's a bug in our understanding. He suggests that underneath all the chaos and probability, the universe is actually as predictable as a clock. This isn't just some argument for the academics. This is a challenge that could spark a revolution in science, forcing us to rewrite the textbooks and rethink the future of technology itself. The quantum world, we thought we knew. To get just how big of a rebellion this is, you first have to understand the kingdom T. Hooft is challenging. For a century, quantum mechanics has been the only game in town when it comes to the subatomic world. Its predictions have been tested and proven right to an insane degree of accuracy. The first is superposition. In our world, things are one way or another. A cat is alive or it's dead. A flipped coin is heads or it's tails. But, in the quantum world, we're told a particle, like an electron, can be in a mix of all its possible states at the very same time. It isn't in one spot. It's a blurry cloud of probability, a wave of potential that covers many places at once. It's only when we look, when we measure it, that this wave of possibilities collapses into one single, solid reality. It's probably the most successful scientific theory we've ever had. And the main version of this theory, the one taught all over the world, is called the Copenhagen interpretation. There's no secret reason the particles showed up here instead of there. It's just pure, cosmic chance. This is the idea that made Einstein so angry, prompting his famous line, "God does not play dice." Here's the gist. If you shoot single electrons at a wall with two tiny slits in it, you'd expect to see two simple lines on the detector screen behind it, right? One for each slit. But that's not what you get. Instead, you get a complex pattern of many lines, an interference pattern. That's the kind of pattern you only get when a wave passes through both slits at the same time and interferes with itself. This suggests each tiny electron, when nobody's watching, is a wave that travels through both slits at once. But the second you put a detector at the slits to see which path the electron takes, the pattern disappears, and you're back to two simple lines. The act of looking forces reality to make up its mind. This has been the strange but accepted truth for 100 years. But for the better part of a century, most physicists have made peace with it, agreeing that the universe, at its core, is a casino. This interpretation asks us to swallow a few ideas that go against all our common sense, and that leads to the second wild idea: indeterminism. The standard view says that the result of that collapse is completely random. The most famous proof of this is the double-slit experiment. The Nobel dissenter, and now, here comes the dissenter, Professor Gerard T. Hooft. This isn't some random voice from the fringes. T. Hooft shared the 1999 Nobel Prize in Physics for his work that helped create the standard model of particle physics, the very theory that describes what everything is made of and how it all holds together. He's a pillar of the physics community. While he doesn't use simple words like nonsense, he argues that the idea of a particle being in many states at once is a literal description of reality. It's more of a mathematical sign that our theory has a blind spot. He believes a particle is always in one definite state and one definite place, whether we're looking or not. What we call superposition is just a mathematical reflection of what we don't know. And he's saying that the central ideas of quantum mechanics aren't just weird, they're probably wrong and are holding us back. In his work, T. Hooft puts a target on the back of superposition. He warns that this faith in quantum weirdness might be what's stopping us from finding the next great breakthrough. To truly move forward and unite our theories of the very small with our theories of the very large, like gravity, he argues, we have to be willing to take quantum mechanics apart and see if there's a simpler clockwork-like machine hiding underneath. From there, his argument gets even bigger. Reality isn't random. T. Hooft believes that underneath the apparent dice rolling of quantum events, there's a deeper layer of reality that is perfectly orderly and predictable. He thinks the universe is a grand machine, running on strict cause and effect, just like Newton and Einstein always believed. The quantum randomness we see is an illusion, created because we're missing pieces of the puzzle. We can't predict what a particle will do, not because it's unknowable, but because we just don't have all the information, and this leads to his most urgent point. By just accepting that the world is random, we've stopped asking the deeper questions. In search of hidden order. So if quantum mechanics is just the fuzzy, statistical surface of things, what's going on underneath? T. Hooft's idea is a return to a concept that has been on the edge of physics for almost a century. Hidden variables. Think about it like this. If you watch someone flip a coin, the outcome seems like a random 50/50th shot. They suggest there are properties and forces we just can't see or measure yet. This was the whole basis for Einstein's famous debate with Niels Bohr. T. Hooft's own idea is based on something called a cellular automaton. Imagine that at the most fundamental level, the universe isn't made of fuzzy probability waves, but a grid of tiny, digital bits, like pixels, on a computer screen. Each bit has a definite state, like on or off, and it changes based on a simple, strict set of rules determined by its neighbors. Einstein was sure that quantum mechanics was incomplete and that we'd eventually find these hidden variables, bringing back a predictable, objective reality. But for decades, this idea was mostly shot down, especially after a physicist named John Bell came up with a clever theorem in the 1960s. Experiments based on Bell's theorem seemed to prove that no local hidden variable theory no theory where influences can't travel faster than light could ever match the strange predictions of quantum mechanics. It looked like the final nail in the coffin for Einstein's view, but that's only because you don't know the exact force of the thumb flick, the spin rate, the air currents in the room. If you knew all of those hidden variables perfectly, you could predict heads or tails every single time. The randomness just comes from your own ignorance. Hidden variable theories say the same thing is true for quantum particles. The quantum weirdness we see would just be a statistical shadow cast by a deeper, simpler, and perfectly orderly reality. We just haven't figured out the rules of the program yet. But T. Hooft and a small group of other physicists think there are still ways around Bell's conclusion. From this simple, deterministic grid, all the mind-bending complexity of the quantum world could emerge, the same way the chaotic patterns of a hurricane emerge from the simple interactions of individual air and water molecules. If he's right, what changes? If T. Hooft is right, this wouldn't just change a few footnotes in a textbook. It would set off a revolution in how we see the universe and what we can do with technology. First, think about the big picture. A predictable, deterministic reality would solve the paradoxes that have given physicists headaches for 100 years. Schrödinger's cat, the famous thought experiment where a cat is supposedly both alive and dead at the same time, solved. The cat was always one or the other. We just didn't know which until we opened the box. The whole mystery of how just looking at something can collapse its wave of possibilities would also vanish. An observer wouldn't be collapsing anything. They'd just be learning the state that was already there. It would mean the universe isn't fundamentally weird. And a qubit, according to the story, can be a 0, a 1, or thanks to superposition, both at the same time. By linking these qubits, a quantum computer could explore millions of possibilities at once, solving problems that would take a normal computer billions of years. It's just unbelievably complex, and we've been staring at its shadow. The technology part is just as big, especially for the promised quantum revolution. Entire industries are betting billions on the idea that quantum weirdness is real. The most famous example is quantum computing. A normal computer uses bits a 0 or a 1. A quantum computer uses qubits, but this whole field is built on the idea that superposition is physically real. If T. Hooft is right, and superposition is just a mathematical description of our own ignorance, what does that mean for quantum computers? He has suggested that the dream of a massive quantum computer that can crack any code might not be possible in the way we imagine. He even points to the constant battle quantum computers have with errors as a potential clue. He argues that trying to correct these errors is basically an attempt to force a messy quantum system to behave itself, a hint that a more stable, classical reality underneath is trying to take over. If he's right, the entire multi-billion-dollar quantum industry might be built on a misunderstanding of how the universe actually works. The great debate, of course, T. Hooft's ideas are still very controversial. The vast majority of physicists stand by quantum mechanics, and for one simple reason: it works perfectly. No experiment has ever broken its rules. From a single particle of light to the chaos inside a particle accelerator, the theory spits out the right answers, time and time again. The evidence seems to show that reality is that weird. So, the pressure is on the challengers. For a deterministic theory like T. Hoof's to win, it has to do more than just sound more reasonable. It has to make a new, specific, testable prediction that the old theory gets wrong. It has to show, in an experiment, where quantum mechanics finally fails. The mainstream argument is that our common sense, which evolved in a big, slow world, is simply the wrong tool to understand the fundamental nature of things. So far, that hasn't happened. T. Hooft himself admits his models are in the early days, and that building a full theory is a gigantic task. But this is how science moves forward. It's not a clean straight line. It's a messy, passionate debate between the established way of thinking and radical new ideas. Every big revolution in science, from Einstein's relativity to quantum mechanics itself, started out as a challenge that seemed impossible. This debate isn't a sign that physics is broken. It's a sign that it's alive and well, still grappling with the biggest questions we can possibly ask. This incredible argument over the fabric of reality is happening in our lifetime. If you want to keep up with the breakthroughs and the big ideas that are changing how we see the universe, make sure you subscribe and hit the bell for more explorations into the frontiers of science. We are at a fascinating moment in the history of science, as 2025 marks the 100th anniversary of the birth of quantum mechanics. It's a time to celebrate a century of discovery that changed the world, but it's also a time of deep rethinking. When one of its own architects is daring to ask if we need to tear it all down and build something new, we're left with two incredible possibilities. Will the next 100 years of physics just add more detail to the strange quantum world we've come to accept? Or, as Gerard T. Hooft suspects, will we finally pull back the curtain and find a predictable, orderly, and shockingly simple reality that was hiding there all along? The search for that answer won't just change some equations on a blackboard. It will change our relationship with the universe and redefine what's possible for humanity. The only thing we know for sure is that the future of physics will be anything but boring.